This is day 3's lesson on 9.1, right triangle trigonometry. We're going to take a closer look today at special right triangles. You might remember Pythagorean triples, where all three side lengths are integers. You might also remember angle relationships, the 30, 60, 90 and the 45, 45, 90. Those last two with the special angles are going to play an important role when we get into the unit circle and when we get into graphing sine and cosine curves. So let's take a closer look.
Some of the special right triangles that we're going to look at have integer side lengths. When they do, those are Pythagorean triples. Some of the most famous are the 3, 4, 5, the 5, 12, 13, and also the 8, 15, 17. Just a hint, getting ready for the SAT or the ACT, these triangles come up very frequently when they're dealing with geometry or trigonometry. We know that these are right triangles because we can use the Pythagorean theorem, hence the Pythagorean triples. Set up those a squared plus b squared equals c squared with the appropriate sides. Perform the square and add those things together, and we'll find that they all work. So you might remember that when we're dealing with right triangles, we are oftentimes asked to solve right triangles. And that means we're going to work to find the measures of all three sides and also all three angles. Looking here, we know in this example that we have all three side lengths, 3, 4, and 5, and we also know that the right angle at C exists. But what about the other two angles? What are their measures? So let's first look to find the measure of angle A. You can see it up in the top corner. And to just go back to some of our trigonometry vocabulary, the sine of an angle is the opposite side divided by the hypotenuse. The cosine of an angle is the adjacent side divided by the hypotenuse, and the tangent is the opposite divided by the adjacent. Since we have all three sides, we're welcome to use any of these three ratios. If any of the sides were missing, that might limit us and force us to use a particular one. But we set these up saying what is our opposite, adjacent, and hypotenuse sides, and we put those into the appropriate locations in numerators and denominators. Just take a second to make sure that all of those are lined up correctly. And remember from geometry that if we know the side lengths of a triangle and we're trying to find the angle, we can set up these ratios, but then to isolate the angle, to say angle A equals, we have to perform the inverse operation. So we would be curious now to know, what is the inverse sine of 3/5? What is the inverse cosine of 4/5? And the inverse cosine of 3/4? If you're going to grab a calculator at this point, please make sure that it is in degree mode. And if you go to generate that, you'll see that all three of these generate the same answer, approximately 36.87 degrees. That should make sense that they are identical because in each case we're trying to solve for A. We don't have to triple our work. We don't have to do this 3 times, but the point is if we know all three sides, we can use any of the ratios. Well, what if we want to find the measure of angle B? We can do similar work. We can say that the sine of B is the opposite over the hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. Just notice now that from B, the opposite side is 4, while the hypotenuse is still 5, and the adjacent side is 3. The hypotenuse is always across from the right angle, and which is the opposite and adjacent sides? It depends on which angle we're talking about. So when we generate these values, we should come out to the same value of about 53.13 degrees. But please don't forget that in a right triangle, the two acute angles are also just complementary of one another. So if one of the angles is 36.87, the other has to add up with it to get to 90 degrees, so it has to be 53.13. We're showing the trigonometry, but there's nothing wrong with just simply subtracting. You might wonder what's so special about the 3, 4, 5 triangle other than the fact that it has integer side lengths. But the idea, remember, about similarity is that if we dilate a shape, if we make it larger or smaller, the shape of the triangle is the same, or the figure, whatever the figure happens to be, which means the angles are congruent and the side lengths are in proportion to one another. So relatively small on your screen now is an 8, 15, 17 triangle ABC. If we wanted to know what's the cosine of angle A, the adjacent over the hypotenuse would be 8 over 17. Right? So we would take a look at angle A, and from angle A, the adjacent side is the 8, and the hypotenuse is the 17. If we want to know what's the measure of angle A, then we would say the inverse cosine of 8/17 gets us to about 61.93 degrees. However, if we dilate that triangle, if we blow it out to the point where we come to triangle A prime, B prime, C prime, it is 3 times as large because you can see 8 times 3 is 24, 17 times 3 is 51, and 15 times 3 is 45. So if we're looking to find what's the measure of angle A prime, and we wanted to use the cosine again, then we locate where that angle is, and we say that our opposite and adjacent sides are 24 and 51. But notice that if our scale factor is 3, we could factor 24 and 51 into 3 times 8 and 3 times 17, lose the 3's, and we come back to exactly the same ratio as that smaller triangle that it was similar with. So now we're going to turn our attention off of Pythagorean triples, where the side lengths are all integers, to triangles that have special angle measures. There are 2 in particular. You might remember these from geometry. The first one we develop by first taking a square. This happens to be 10 by 10. If we have that square, I'd ask you now to draw yourself a diagonal from one of those vertices to an opposite side. That creates triangle DEF. If we just shade out that G, don't worry about the other half of the square. We're just going to focus on one triangle. What's the length of the diagonal? How long is that? Well, we have the ability to do the Pythagorean theorem, a squared plus b squared equals c squared. And rather than saying 100 plus 100 equals 200, I'd like to keep that as 2 times 10 squared. And the reason is, in the next step, we want to take the square root of both sides in order to find out the hypotenuse. We don't want the hypotenuse squared, so that's why we take the square root. That leaves us with plus or minus the square root of 2 times 10 squared. So I hope that's easy enough to see why the 10 comes out. Also, although algebraically the plus or minus makes sense, if we're talking about the length from D to F, we would go to the positive. So if we have legs that are 10 and 10, we have a hypotenuse that is 10 radical 2. In general, if we have the side lengths that are x and x, we're going to have a hypotenuse that is x radical 2. So if we want to fill that in, we've got legs of 10 and the hypotenuse of 10 radical 2. So when we drew that diagonal through the square, didn't we take 2 90-degree angles and bisect them? Therefore, triangle DEF has angle measurements of 45, 45, and 90, and you can still see those side lengths. One way to think of that is that if we have an isosceles triangle, then angles D and F are the same. Angle D plus F plus 90 equals 180 degrees. Since D and F are the same, we should be able to say that 2 times angle D equals 90 degrees, so angle D equals 45. So too angle F. Another way to think of it is that if we were to take the tangent of angle D, then the opposite side is 10 and the adjacent side is 10, so the tangent of D equals 10 over 10, which equals 1. Grab your calculator and figure out what's the inverse tangent of 1, and you'll find that we are looking at 45 degrees. Or, if you want to do something alternatively, you could say, what about the sine of D? The opposite over the hypotenuse would be 10 over 10 radical 2. And notice that the 10s cancel out, simplify. So the sine of D is radical 2 over 2 if we rationalize the denominator. Throw that into your calculator with the inverse sine, and you'll also find out that that's 45 degrees. Again, not to say that you have to do this 3 different ways, but it's just affirming that multiple methods are possible. So from a square, from a regular quadrilateral, when we created the diagonal and bisected the right angles, we found out that they were 45 degrees. So what we're looking at here is a 45-45-90 triangle. It's also known as an isosceles right triangle. And the pattern with leg lengths is that if one of your legs is equal to, let's just call it leg, then the other leg has to be the same in this triangle because they're congruent. And the hypotenuse is going to be whatever that leg equals times radical 2. So we have 10, 10, and 10 radical 2. We could have had 17, 17, and 17 radical 2. We could have had 3.4, 3.4, and 3.4 radical 2. Any side length for a leg is going to be the same as the other leg if it's isosceles, and the hypotenuse will be that value times radical 2. Also, what's useful for us going forward will be to understand that if the hypotenuse happens to be some value, some hypotenuse, then both of the legs are that value times radical 2 divided by 2. Therefore, if we were to say something like, what if the hypotenuse was 12? Then 12 over 2 is 6. Each leg would be 6 radical 2. If our hypotenuse was 7, then our legs would be 7 radical 2 divided by 2. We looked at one special right triangle based on angles, the 45-45-90. There's one more to go. You might remember what it is. We create it by first creating a regular triangle, an equilateral and equiangular triangle. So all 3 sides are the same length. In this case, they are 8. And all 3 angles are the same. 180 divided by 3 equals 60. Angles Q, R, and S are all 60 degrees. Now, if we take the opportunity here to draw an altitude, let's say from S, that altitude means that it's going to come and serve as the height of the triangle. It comes from that highest point at S, and it comes down and meets QR perpendicularly. That happens to also be an angle bisector, so angle S is cut in half, and a segment bisector, which means QR is cut in half. So it used to be 8 units long. We can now see that QT is 4 and RT is also 4. The 60-degree angle up at S has now been bisected, so we have 30 degrees and 30 degrees. Well, what's the length of the altitude from S down to T? How long is that? If we have a short leg of 4, a long leg of ST, and a hypotenuse of 8, how do we find the long leg? Use the Pythagorean theorem. So 4 squared plus that long leg squared equals 8 squared. So 16 plus b squared equals 64. Bring the 16 over to the right. Take the square root of both sides. We get plus or minus the square root of 48. 48 happens to have a perfect square, 16 times 3. Again, we're talking about a side length, so we disregard the negative value. And that side length is 4 radical 3. Therefore, if the short leg was 4 and the long leg was 4 radical 3, that leads us to a pattern. Leg radical 3, and the hypotenuse, how do we get from 4 to 8? We double it. So whatever our short leg is, in this case 4, our long leg is that number times radical 3, and our hypotenuse is 2 times 4, or just simply 8. So from a regular triangle, when we created that angle and or bisector, we took the 60-degree angle at the top, we bisected it so it's 30 degrees. We created the altitude, which is perpendicular, that's 90, and we didn't touch angle R, so we have what's known as a 30, 60, 90 triangle. And the patterns to consider are that if we have a short leg of just, let's call it leg, then the long leg is that value times radical 3, and the hypotenuse is that short value, that short leg, times 2. It's also true we can work the other way. If we know that the hypotenuse is some value, then the short leg is going to be half of that, and the long leg is going to be that value, the hypotenuse divided by 2, times radical 3. Seeing it this way will help us a little bit more as we get into our trigonometry. So here is that same triangle over on the right again. Triangle SRT has those 3 side lengths. Can we figure out what the angle measurements are? I think we already know what they are, but we can use the trigonometry to just confirm, to strengthen our understanding, and to help us develop ideas going forward. So let's talk about the sine, the cosine, and the tangent. Remember what those ratios represent. Remember how to spell SOHCAHTOA, S-O-H for sine, C-A-H for cosine, and T-O-A for tangent. If we plug in the values there, from R, the opposite side is the 4 radical 3, and the hypotenuse is 8. For the cosine, the adjacent side is 4, and the hypotenuse is still 8. And for the tangent, we get 4 radical 3 over 4. Notice all 3 of those ratios can reduce. So the 4 and the 8 can reduce to 1 and 2, so the sine of R is radical 3 over 2. The cosine of R can just be 1/2, and the tangent can just be radical 3. It's real nice that those things can simplify. It brings us back to the idea of the dilations. We could increase the size so that the small side was 6, then we would have 6 radical 3 and 12. We could go out to 19, then the long leg would be 19 radical 3, and the hypotenuse would be 38. The pattern always applies. If we go to take the inverse sine, cosine, and tangent of those respective values, each one will give us precisely 60 degrees. So you may not be in love with the radical 3, but it turns into a triangle that's a 30, 60, 90, quite beautiful. Where we may not be in love with 36 and 53 degrees with some decimals running after those Pythagorean triples of 3, 4, 5 or 5, 12, 13, those are real nice values to be dealing with. Here is this section's core concept related to the trigonometric values for special angles. For the 30, 45, and 60 degree measurements, we can look at the sine, cosine, tangent, and even the reciprocal ratios, the cosecant, secant, and cotangent. And notice things like the complementary angles. Look at the sine of 30 degrees and look at the cosine of 60 degrees. They're both 1/2. Look at the sine of 45 and the cosine of 45. Those are complementary angles, and they are equal to one another. Look at the sine of 30 and the cosecant of 30. Notice that 1/2 and 2/1 are reciprocals, and we can make similar connections throughout. The more you understand this table, the quicker you'll be able to evaluate things going forward. Can we use our understanding of trigonometry to solve this triangle ABC? Meaning, can we find the 1 missing angle and the 2 missing side lengths? Well, make your life easy. It's a right triangle, so the 2 acute angles are complementary. One of them is 60, the other must be 30 degrees. What about the hypotenuse? If we want to employ some trigonometry, the only side length that we currently know is 7 radical 3, and that's opposite 60 degrees. If we're looking for the hypotenuse, O and H lead us to the sine. Sine of 60 equals 7 radical 3 over the hypotenuse, AB. A little bit of cross multiplication leads us to the hypotenuse equals 7 radical 3 over the sine of 60. And if we generate that with a calculator, we'll find out that AB equals 14. If we want to find that other side, BC, I want to use 30 degrees this time. So up at angle A is 30 degrees, and the opposite side is BC, and the adjacent side is 7 radical 3. Now to get the opposite side by itself, all I need to do is multiply 7 radical 3 to the left, generate that answer, and BC equals 7. But don't we already know that this was a 30, 60, 90 triangle? Aren't we aware of the values? Whatever the short leg is, the long leg is that times radical 3, and the hypotenuse is 2 times that. We were given that the long leg was 7 radical 3, so the short leg needs to be just the 7, and the hypotenuse needs to be the short leg times 2, so we get 14. And here's that 45, 45, 90 triangle with a hypotenuse that's an integer, 3 units. How are we going to be able to figure out what the two sides are, AC and BC? Well, using trig ratios, we can say that the cosine of 45 degrees is the adjacent side over 3, the hypotenuse. We can multiply the 3 to the other side and find out that AC and BC are both approximately 2.1213. Grab a calculator and just confirm that. But we also have the special right triangles. We have a 45, 45, 90 triangle, and we know that the hypotenuse is whatever the leg is times radical 2. Well, we're looking for the leg. 3 is equal to the leg times radical 2, so we should be able to say that the leg is equal to 3 divided by the square root of 2. If you want to go ahead and rationalize that, then AC and BC are both exactly 3 radical 2 divided by 2. Here's an interesting thing. Grab your calculator and see what that is approximately. It should be the exact same number as we saw over in the left column. And also, don't forget that the Pythagorean theorem works also. If we want to say a squared plus b squared equals c squared, but knowing that the two legs are the same, then a squared plus a squared. Simplify just by saying 2a squared equals 3 squared. Work to get a by itself, so a squared equals 9 divided by 2. Take the square root of both sides, and we should get plus or minus the square root of 9/2. The square root of 9 is 3. Radical 2 is in the denominator, and we're going to go with the longest side. We should really rationalize that denominator. When you do, I hope you'll confirm that that is exactly 3 radical 2 divided by 2, and it is the same approximation that would come out when you multiplied 3 times the cosine of 45 degrees. But once again, there's a special pattern here. Make sure we understand this. The 45, 45, 90 triangle can be x, x, and x radical 2. If we happen to know, like in this case, that our hypotenuse is a integer, then I'm just using a different variable here. Whatever the hypotenuse is, the two legs are half that number times radical 2. So we had 3 for our hypotenuse. So our values were 3 divided by 2 times radical 2.
Thank you for watching this last day of 9.1 right triangle trigonometry. In our next section, we'll be talking about angles and radian measurement.